In this fifth workbook problem, we're asked to consider a delta y equals 0 two-dimensional projectile motion problem. Specifically, there's some football quarterback who throws a pass to a receiver, and the receiver catches the ball at the same height from which it was thrown. The initial velocity is 22.5 meters per second, and the throwing angle is about 63 degrees above the horizontal. So to begin this problem, I'm going to just diagram out what I see, and what I'm visualizing is the football player throwing the ball, and then someone else catching the ball. And the initial velocity vector looks about, say, there's 45 degrees, so maybe that's 63 degrees approximately. And the ball is actually going to make this sort of a two-dimensional projectile parabolic path. I'm not going to draw that in there. I'm just visualizing that, and instead I want to start by not working in 2 dimensions, but in 1 dimension twice. So I want to work in the vertical dimension to figure out in part A the total time in free fall, and then the horizontal dimension to figure out things like the range, say. So let me start by decomposing this velocity vector into its x and y components. I'll label the hypotenuse what it really is, v naught x, the true initial velocity vector, and then the horizontal component is going to look a little something like, say, that, and then the vertical will look a little something like this. I'm going to label those parts as well. So now that I've labeled the x and y components of velocity, what I'm going to do is just work in the vertical dimension to figure out the total time in free fall. So the first thing that I'll do is get rid of my little player over there and make a list of initial conditions. So I'm going to start in the vertical dimension, and maybe I'll write in red to be consistent just for fun, so we'll see how that works out. In the vertical dimension, I'm going to start with y naught and y final, and then the initial velocity in the vertical dimension, v naught y, v final y, ay, and t. And I'm not sure what height the football quarterback releases the ball, but since I know it's caught at the same height, I'm just going to set that to be 0 meters high. I could set it to be 10 meters high. And if I did, I'd set this to be 10 meters high as well. The catching height, the difference between those two would be 0. So why not just make it simple? Why not just make each 0 meters high, and then the difference between those two is still 0. The more things I have that are 0, the easier it is to work the problem. Now the y component of velocity, v naught y, that part right there, that length is opposite to the angle. There's the angle, and that length is opposite to the angle. It's so far away from the angle that I'm going to use the rule of hypotenuse times trig function, and the trig function I'm going to use is the sine function because it's the opposite side of the angle and it's so far away. I needed a sine to find its length. And then v final y. Now from our discussion in class, we know that that's really negative v naught sine theta. And you can certainly go ahead and use that. But I'm not going to use it right now. I'm going to pretend like I don't know what it is and develop that idea later on just to make sure that you've seen it before. So that's unknown to me, the final catching height, the final catching velocity in the vertical dimension. G is what I've got here. And numerically, we're using negative for the direction, 9.80 meters per second squared for the units, and the time is what I'm looking for in part A. So what this leads me to is a desire to know this quantity, but no knowledge of that quantity there. So what I'm going to do is choose a kinematics equation that will help me do that. And the one that comes to mind is the big dog displacement equation. So let me write that down. So I'm looking at y equals y naught plus v naught yt plus 1/2 gt squared. Big dog displacement equation. And what's nice about this for us is that this value and this value are all 0, or both 0. So the result of that is 0 equals V0 sine theta times t plus 1/2 gt squared. So what I'm doing is I'm asking the big dog displacement equation, at what time t is the initial position equal to the final position? And what the displacement equation returns is, well, 2 times. So if I factor out a t, which the t factor exists in each of the terms, if I can factor out a t, I'm left with the initial y component of velocity, v0 sine theta, plus a 1/2 gt term. So in order for this combination of factors, the t and the binomial, to multiply together to be 0, one of the 2 factors has to be 0. And so I'm thinking it's either this one or it's this one. V0 sine theta plus 1/2 gt equals 0. So both work. It turns out when t equals 0, that's the very first time the final height and the initial height were the same. Like right here, at that time, that's t equals 0 seconds at the launch, and then later on in time, over here, is when the landing height is the same as the launching height. So that corresponds to this equation here and the 0 for that equation. So let's work out that detail. Let's see, I've got, how about just subtracting this term from both sides? 1/2 gt equals negative v0 sine theta, multiplying by 2, negative v0 sine theta, oops, there's a 2 in there, and then finally dividing by g, negative 2 v0 sine theta over g. All right, so that's the total time the object is in free fall for. At that time, at this time, that's a launching time, and this is the landing time. So let's calculate the landing time. The landing time comes out to be 2 times 22.5 meters per second times the sine of 63 degrees divided by 9.80. I let the negative sign of the g cancel out with the negative sign here, and I end up with a total time of almost 4.1 seconds, 4.9 seconds, rounded to 3 significant figures. And then I'm incredibly excited about that result, so I'll put a box around it. I'll write something meaningful here, like total time in free fall. So that's the answer to part A. It's a little bit of a long way to go about getting it, but that's important. We took the time to go through that. So 4.09 seconds is the time between the throw and the catch. And let me condense that to something. Put it someplace. Put it here for now. And we'll look at that later. All right, so what I'm looking to do next is calculate the ball's velocity at the apex of its parabolic trajectory. And that should be relatively simple because the entire time the object has been in free fall, the x component of velocity has been constant. And at the apex, the definition of the apex is the y component of velocity there is 0. So that's just a simple it's not even it's nothing to do really, it's just a concept. V at the apex is equal to v naught x in magnitude. The direction is at 0 degrees, so I'll simply take v at the apex and calculate the speed portion, v naught cosine theta. It's still directed that way. Long-winded here, but we'll get to it. V naught x, 22.5 times the cosine of 63 degrees turns into a 10.2 meters per second at 0 degrees. You can do that in one line if you'd like. I'm just having a bit of fun. So this would be the, what would that be? The velocity at the apex. And now that we're done with that idea, I'll shrink that one down and put it away as well. And let's look at part C. Calculate the final velocity just before the receiver catches the ball. That's going to be fun. Let's take a look at this one. So here's that concept again. Hey, where did it go? Hold on a second. Let me get rid of that one again. Yo. Enough of that. Stay. Okay. The final velocity just before the ball is caught. So that's what we're looking at. Something like this. The ball would be caught right about here. So I'll erase these parts. And alright, so right at this spot, the x component of velocity is still the same. It's however long it was, about that long. That hasn't changed. So that's still Vx. And what has changed is the y component of velocity. The y component of velocity started large, and then it shrunk down as it got to the apex. And then from the apex it starts pointing back down again. And now we're over here. So once we're back at the same height that it was thrown at, what I'm going to try to show you is that the y component of velocity is the same length. And as a result, the final velocity vector looks just like the initial velocity vector, just pointed in a different direction. So check this out. This will become v final y, and what we're looking for is that guy right there, which is v final. V final vector. Alright, and this is the angle inside of here. I'm going to give it a different symbol. I'm going to call it phi. Just a different symbolic notation for the final velocity vector's direction. Check this out. So we know that v final in length will follow the rule of the Pythagorean theorem, where you get vx squared plus vy squared equals the final speed squared. So what I need to do is, of course, take the square root of both sides to get the actual speed. And this part hasn't changed. That's still v naught x, v naught cosine theta, whatever that 10.2 meters per second was. And this is the part that's changed. V final y, let me step over here for a minute. V final y is equal to v naught y plus gt. That's might be our first equation of kinematics, or first or second one. So what I'm going to do is exploit that idea. What I'm looking for is this final velocity at the end of time for this particular problem. So I've got this, g, and t was that negative 2 v naught y over g. That's what we found earlier in the problem. Well, if I work out these details, this g and that g cancel, and one's in the numerator, one's in the denominator. Vy, transcribing v naught y, and then what I end up with is negative 2 v naught y. And so I have a whole something minus 2 of the same things. The result of that is that Vy at the end of the time for this particular problem is equal to the opposite of the initial velocity vector. So that's an important result. That just means that I can take this thing, which is the final vertical velocity, not the total velocity, just the vertical component, final vertical velocity, and I can substitute it right into here, negative v naught y, and then square that quantity. Now what's cool about this is I know v naught y. That's something I worked out earlier. And the square here, acting on the parenthesis, squares what's inside, including this negative sign, to turn it into a positive. Oh, isn't that cool? So what I end up with there is essentially just v final equaling the square root of vx squared plus v naught y squared. And that is, well, I should be careful about this. Since Vx hasn't changed, it's just like V naught x. And what I have here is the Pythagorean theorem applied to the initial velocity vector. And so that's telling us that the final speed is the same as the initial speed. So I can just write down V final equals 22.5 meters per second. That's the final speed portion of the final velocity vector. Final speed. So I'm going to take this last little piece and put it down here again, in case I need to use it again, and then focus on this angle. Focus on that angle. Whoa, that might have been a mistake. Focus on that angle inside of there. So that angle inside of there is going to come to us from an inverse tangent argument. So the angle in question, phi, is defined by the inverse tangent of the opposite side of that triangle, v naught y, v naught x. And then of course I'm really looking at v final y, which is opposite of v naught y. And so the result of that calculation, since tangent's an odd function, it's going to spit back a negative number, and it'll come up with negative 63.0 degrees. And that's the direction, right? So that's final direction. So I can condense all of that stuff. Condense it all down to some little tiny amount. I'll put it down here someplace. And I will try to erase some of this stuff that's in the way. Just summarize the final velocity to be v final vector equals 22.5 meters per second at negative 63 0.0 degrees. And call it the final velocity. Whew. All right, moving on. What else can we do? What's the next step? Oh, the range of the football. Yeah, let's switch over to the range, sure. A list of initial conditions in the horizontal dimension. I'll start with, x naught, x, v naught x, vx, ax, and t. Now, we already know what t is. We found that out earlier. It was 4.09 seconds. There is no horizontal acceleration in free fall problems. That's nice. Vx and v naught x are the same since there is no acceleration. That's the v naught cosine theta idea, which we found out before was 10.2 meters per second. 10.2 meters per second. X is what we're looking for, the total range, and then let's have the object start at 0 meters, since we get to decide that. With that list of initial conditions, I'm led to choose something like x equals x naught, v naught xt, 1/2 ax t squared. That term instantly goes to 0 because the acceleration is 0, and I chose this to be 0. So now I just have summarize this. V naught x times t is as simple as, well, I'll write it out. V naught cosine theta or was 22.5 meters per second times the cosine of 63 degrees times 4.09 seconds. And the result will be some sort of a monstrous range. 41.8 meters. Monster pass. And that's the range. Horizontal displacement during free fall. Delta x. Boom. Cool. And let me take that piece, move it someplace here, access it later on if necessary. Still working at the details of how we're going to solve these problems on this screen, but that's what I got so far. I'm going to move this guy out of the way. Take him and shrink him down. All right. Now the final thing to do, part E, the acceleration during free fall. I just threw that one there just to constantly remind you that the acceleration any time during free fall is equal to the vector sum of ax plus ay, and of course ax is 0, so that doesn't count. And so the total acceleration is just equal to the vertical acceleration, which is just equal to g, which would be a equals 9.80 meters per second squared. And then just to be clear, put it at 270 degrees. So I'm not going to put the negative sign in front because that's not clear in 2 dimensions if I mean downward or leftward. So here's the free fall acceleration. All right. So don't forget, as long as the object is in free fall, if it's anywhere between 0 and 4.09 seconds, it's free falling, and that is the acceleration, free fall acceleration. That's our model, our simplistic model of projectile motion. High school physics works great for a decent approximation to reality. As long as things are moving slowly and highly aerodynamic, bam. Alrighty then, last piece is the kinematics graphs. Let's draw them up, sketch them in. Alright, so here are the kinematics graphs. Let's look at the acceleration of the vertical dimension, velocity in the vertical dimension and the vertical position, and AX, VX, and X. So the easiest ones to look at, I think, for me, are the x-axis, the horizontal vectors. So I'm going to draw those first. Make my pen a bit thicker. So I've got AX, 0, straight away, just 0. No acceleration side to side, so I got a 0 value there. And then the x values of velocity are constant, so a nice horizontal line of the constant value, and then the horizontal displacement is linearly increasing with time. And then AY, similarly, is constant, but negative. It's not 0, it's negative 9.8 in the vertical dimension. And then the y component of the velocity, it starts positive up here, and then it goes to 0 at the apex, and then it goes to negative at the bottom. So at the end of time, it's going the same speed but in the opposite direction, so I try to make sure that this is just as far below the line as that is above the time axis. And then, whoops, the position function, that guy simply starts at the ground level, ends at the ground level, and goes up to some apex and back down again, like a parabola. Whew! All right, well, that was a long-winded one big movie for the solution of problem number 5. If you had the time in your life and you're not asleep, try to solve problem number 6. Good luck.